Welcome to Metal Casting Lecture Series by Professor Joyjeet Ghose. This is the 12th lecture of a series of lectures. This lecture will be on design of sand casting riser. Various methods of riser design will be discussed in detail. Examples of Modulus method of riser design will also be discussed. So, do not miss and watch the full video. For the next video in the lecture series, please click the suggested video link above. You may also click on the playlist at end of the video to access all the videos. Please subscribe this channel and yes, do not forget to like and share. Also click on the bell icon to receive instant information of new videos uploaded. Thank you.
Hello friends, welcome to this 12th lecture of a series of lecture on metal casting. In this lecture, we'll be discussing about riser design. So before we start discussing what is riser design and aspects of riser design, we should know what is a riser. Riser, which is also known as a feeder, is basically a reservoir, a cavity which is built in the mold and which stores the molten metal, and it supplies the molten metal when there is liquid shrinkage of the molten metal in the mold cavity. Now what happens? The liquid metal, when it starts to freeze, it will increase its density, therefore it will shrink. Now when it shrinks, there should be enough metal in the riser to compensate for that shrinkage. So riser is an extra void, or you can say it's a reservoir, it's a feeder which is created in the mold to compensate for liquid shrinkage of the mold or the molten metal inside the mold. Now riser has, apart from this function, it has also another secondary function, that is it must be kept, if it is open, it's a open riser, then it maintains a positive pressure of the liquid. And if it is open riser, then the foundry man, if it is done manually, can look at the riser, and if the molten metal is coming out to the riser, the foundry man can understand whether the mold has been filled or not. And an open riser allows the gases, it acts as a vent and allows the gases to escape. Well, of course, these are secondary functions, these are not that important, but the important function is that riser acts as a reservoir of molten metal, and it supplies the molten metal during the liquid shrinkage of the metal in the mold. Okay, some important aspects of risering design is that the volume of the riser should be enough to compensate for the total metal contraction near its placement. So if the casting is large, there can be more than one riser. So maybe a riser is not enough to compensate for the entire contraction of the casting. So normally we have one or more riser depending on the size of the casting. It should have enough liquid metal to compensate for the shrinkage. So if riser is not there, so what will happen? It will result in a shrinkage cavity. So riser is there to prevent the shrinkage cavity. And it is very important that the riser should be designed in such a way that the metal in the riser solidifies at the end. It is by design. We can of course provide thermal covering and all these things, but it should be designed in such a way that the riser should solidify at the end. That is, riser should be effective in establishing a pronounced temperature gradient within the casting, so that the casting will solidify directionally towards the riser. That means the metal in the riser will solidify at the end, and accordingly this is achieved by the shape of the riser, by the size of the riser, and by the location of the riser. The shape, size and locations are very important in riser design. So there are various types of risers. It can be a top riser. If the riser is placed on the top, it is called top riser. If it is placed on the side, it is called side riser. And if it is blind, it is not open to the atmosphere, it is called blind riser. If it is open to the atmosphere, it is called open riser. and there can be a hot riser and it can be cold riser. Hot riser means it receives the hot metal at the end. And whereas a cold riser is filled before the mold cavity. So the mold cavity is filled through the cold riser. That type of riser is called cold riser. So depending on where it is placed, whether open or not, whether hot or cold, so risers can be named in different ways. Now, one important aspect, riser shape. A riser shape can be cylindrical, it can be rectangular, it can be a square cross section, doesn't matter. But what matters is that the ratio of the volume of the riser to the surface area, that matters. That decides the surface area of the riser, that decides the solidification time. Now obviously if it is cylindrical, the surface area will be lowest, and if the surface area is lowest, the volume by surface area ratio will be highest, and therefore normally the riser shape is cylindrical. Okay, size will be decided by riser design. What should be the size of the riser? And normally it varies from the height by diameter ratio, h by d ratio of the riser varies from 1 to 1.5, sorry 1 to 0.5. So h can be equal to diameter, or h can be equal to half the diameter. So it should be within this range. It is normally prescribed so that the riser solidifies at the end. And where should you locate the riser? Obviously you will locate the riser in the heavy section, near the heavy sections, where there will be much more shrinkage. Now to compensate for the shrinkage, riser will be placed near the heavier section of the casting. So these three are important. So basically what we learn now is that riser location is okay. It depends on your casting shape, which section is heavier you will be placing it. What should be the shape? We have come to a conclusion it should be cylindrical shape, because the ratio of V by A will be highest, and we will decide, we will learn how to design the riser size. How to decide the riser size. So that can be done by three methods, which is called Cains Method, Modulus Method, and Nebel Research Board Method. So we'll be discussing the Cains Method first, then we'll be discussing the Nebel Research Board, and we'll discuss the Modulus Method and we'll solve some numericals based on Modulus Method. So in Cains Method, what happens? Cain in 1952 came up with a formula to find out the freezing ratio. Now this all depended on the Sovereign's rule of the solidification time, or the ratio of V by A. So the freezing ratio X is equal to A by Y minus B plus C, where A and B are certain constants related to freezing characteristics and solidification contraction, and C is a solidification rate relative measure, and Y is what? Y is the riser volume by the casting volume. So we have X and we have Y, so we have to plot X and Y in a graph as given by Cain. Cain has done several experiments. So these are the guidelines for finding out the value of A, B and C. So A, B and C you can take from this table depending on the material you are casting, and you plot X and Y values. You can find X once you have the values of X, values of Y, A, B and C. You can find out X. Once you have X, you plot X and Y in this curve. Now if the X and Y for your riser falls on this side of the curve, you can expect a sound casting. If it falls on this side of the curve, you can expect shrinkages. Now this method is not a method to design the riser. Rather, it is a method to test whether your riser design is okay or not. First, what we have to do is that you have to design a riser dimension, come to a conclusion of your riser dimensions, and from that riser dimensions you calculate the riser volume, and using the riser volume you know the casting volume, so you can find out Y. So for your riser you calculate the Y and then you calculate the X. So for that X and Y you plot here. So if an X and Y plot is on this side, you can expect a sound casting. On this side, you can expect a shrinkage. So this is the Cains method. And in Nebel Research Board method, what it was developed by Bishop in 1955 of Naval Research Laboratory. In this method, he has again, this is also based on S by V ratio, V by A ratio. Basically, we find out the shape factor. What is the shape factor? Shape factor is basically the length of the casting plus width of the casting by thickness of the casting. So this we can understand with an example. I'll show you an example here. Suppose this is a plate of length 20 inch by 20 inch into 2 inch. Okay. So here the length is 20, the width is 20. So L plus width is 20 plus 20 by thickness is 2. So we get here 40 by 2, that is 20. Now this 20, this is a curve of shape factor and the ratio of the minimum riser volume to the casting volume. So this 20 I have this 20 point I have plotted here. So it touches this line, this curve at this point. So if I take it here, so this comes out to be, this ratio comes out to be 0.25. The ratio of what? The ratio of the riser volume by the casting volume. So VR by VC, ratio of the riser volume by the casting volume, which is equal to 0.25. And I know my casting volume. What is this volume? 20 into 20 into 2. So that gives me 80. So, so 800, sorry. So 800 into 0.25 will be 200. My riser volume is 200. Now I know my riser volume. Now what I am interested in is that I also know that it is a cylindrical riser. I am interested in finding out the diameter and the height. Okay, now there is another curve. You will plot this 200 here and draw a straight line here, perpendicular straight line. So here it is the riser height in inches. So this is given height and this is the diameter. So various lines for diameter. Now you can select a diameter of 6 inches and height will be 7 inches. That is possible. Okay, but that is not recommended one, because our recommended height by D ratio of riser is 1, or it may be within this 0.5. So it should be within 1 and 0.5. So you can go for these 8 inch or 7 inch. So if I take a 7 inch, then it is coming out of slightly more than 5. So let's say 5 and 1/4 inch. So diameter is 7 inch and height is 5.14 inch. So if you take this, then you are in a comfortable zone and you expect the riser will solidify at the end. So this method is called the Naval Research Laboratory method. But much more popular method is the Modulus method. Now what is this Modulus method? So Modulus method is based on this Sovranov's rule, Sovranov's rule of this casting. So here it is solidification time of the riser. So we'll design in such a way that solidification time of the riser is at least 20% longer than the solidification time of the casting. Now we have defined a term called modulus. Modulus is V by A surface area of the riser and V by A surface area of the casting. So if this is proportional to that, we can say M is V by A of riser is also should be proportional to 1.2 times the modulus of the casting. So M riser should also be almost equal to 1.2 times the casting modulus of the casting. Okay, so for a cylindrical riser, so modulus will be, you can calculate it, it should be dH by twice H plus 2D. So this will be using, we can find out the modulus of the casting and multiply it by 1.2 and we can find out the modulus of the riser. And from the modulus of the riser, we can take a H by D ratio, appropriate H by D ratio, either H by D ratio is equal to 1 or H by D is equal to 0.5 or anywhere between 1 and 0.5, and accordingly we can find out the dimensions of H and D. Now one thing is very important from this, we are not aware whether the volume of metal in the riser is enough to compensate. For that there is another formula, Vmax is equal to V riser 14 minus S by S. This S value we can calculate from this curve for different material, contraction volume, and from that we can calculate the Vmax. Now if Vmax is less than the casting volume, then we can say that we have enough material in the enough material volume in the riser to compensate and this will be the maximum volume that the riser can compensate. If this maximum volume is more than the casting volume, then it's okay. So in case this maximum volume is less than the casting volume, then we have to redesign it. So let's discuss a problem, then you will be able to understand. So there is a lever here whose volume is 0.955 inch cube and surface area is 6.905 inch square. Now we have to design a riser. So riser is placed here. This is the heavier section. So riser is placed here, and we'll find out the dimension of the riser. So we can take the modulus of the riser is equal to 1.2 times the casting modulus of the casting. It comes out to be 0.1660, and the modulus of the riser can be this in this manner. It will be dh by 4h plus 2rd, and if I take h is equal to h by d is equal to 1 or h is equal to d, so from that we can calculate d is equal to 0.996 and h is equal to 0.996 inch. From that we can calculate the dimension of the riser. Now whether this riser volume is enough to compensate for this volume, we can check in this manner. We can check out the Vmax by the formula considering this aluminum alloy. So S is 3.8, so V riser is this, so it comes out to be 2.08 inch cube. So this 2.80 inch cube is much more than 0.955. So therefore enough volume of material is there in the riser to compensate. There is another problem. A cylindrical riser must be designed for sand casting mode. The casting itself is a steel rectangular plate with dimensions 7.5, 12.5 centimeter and 2 centimeter. The previous observations have indicated that the total solidification time of this casting is 1.6 minutes. The cylinder for the riser will have a diameter to height ratio d by h ratio is equal to 1. That means d is equal to h. Now determine the dimension of the riser so that the solidification time is 2 minutes. First, you have to calculate this modulus. So V is of the casting is this much, and surface area of the casting will be this much. So, and time taken is this. We can calculate the mole constant. So mole constant comes out to be 3.26. So once we have the mole constant, so this we can use to calculate the riser dimensions. So riser dimensions will be, for a cylindrical casting, it will be, considering that d is equal to h, it will be d by 6. So d by 6 square into the mole constant is equal to 2, because we want the solidification to be 2 minutes. So from this we can calculate the dimension as 4.7 centimeter, and similarly the height will be 4.7 centimeter. Okay, so with this we come to the conclusion of this lecture. I hope the concept of riser design is clear to you. If you have any doubt, please feel free to put it in the comment box or contact me, and I will try to clear the doubt. Thank you for watching this video.